This is the third video on chapter 40, the Riemann integral. And again, we're focusing on the area under the curve. And this is the same picture that I had in video number 2. So in part 2, I've left this picture up here. And what we did in the first video is we focused on the area of this one part right here, and we've said that was approximately the area of the rectangle that we have here. So we took this rectangle and we said that is approximately, the area of this rectangle is approximately the area of the region bounded by this vertical line, in the graph of our function. That's what we did in the second video. What we're doing in this video is we want to talk about the entire area under the curve. So we want to look at the region that's bounded by the curves x equal to a, x equal to b, and y equals f of x. We're going to let a represent that area. So that is the area of the region bounded by these three curves. And of course the y-axis. So in all three of these videos so far, the two videos where we're talking about the area under the curve, we're assuming our function's above the x-axis because we're talking about the area under the curve. We'll talk about functions that go below the x-axis later, but we haven't talked about that yet. So we're just talking about the area of this region. That area is approximately the sum of the areas of the rectangles. So we take the sum I equal 1 to n. So remember, I starts at 1, goes to n. So we're going to do this for every single rectangle now. So for every single one of these that are drawn here, so we've picked a representative point, x sub I star, as the height of our rectangle. The width is delta I. And so what we do here with this summation is we're adding the areas of all those little rectangles. And we're saying the area of that region is approximately that. We're approximating the area with the sums of the areas of the rectangles. But we don't want to approximate the area, we want the actual true area. So what do? We take smaller and smaller rectangles. So we let these lengths go to 0, and then we chop this up into much smaller pieces. And so to do that, we take the limit as the length of our partition goes to 0. So remember what the length of the partition is. It's the max of the delta i's. So we have the largest delta I. We have these getting very small. So the max of the delta i's are getting small. That's what this means. And then we take the areas of the rectangles. But because we're passing to a limit now, we're taking this limit. As the length of the partition goes to 0, this is the true area. And so what we have done is we've taken this interval and we've just chopped it up into smaller and smaller and smaller rectangles. And that gives us the true area.